Yeah, our next speaker is Professor Jip Park from Hanyang University. And he's going to tell us about magic angles of 3C bilayer magnetic material. Let's welcome the speaker.
First of all, I would like to appreciate the organizers in both Deja and Dresden for this very interesting experimental workshop. So I'm very excited. Today, I'm going to talk about the magic angle of twisted bilayer magnetic materials. So it has been quite a while after this big explosion of the study of the twisted bilayer graphene, and there were many follow-up studies. So as one of such extension, today I'm going to talk about the spin system. What happens if we consider a twisted bilayer of the spin system? That's the question that I'm going to answer. Okay, so before I start my talk, I would like to first acknowledge my collaborators. So Dr. Kyungmin Kim from PCS IBS is the main player. He has done all the difficult computations and all the work. And also we have Professor Myung-Jun Han and Dong Kim from KAIST. They did the first principles calculation. And we also had an interesting discussion from the Professor Taekwon Kim and Dr. Kyung-Jun Ko from the KAIST. Okay. So in physics, there are many different length scales, and these length scales typically determined by the interactions and fluctuations in the system. For instance, in these solid state lattice, atoms interact through dipole-dipole interactions, and these dipole-dipole interactions makes this interesting crystal, and this typical distance between the atoms are determined by these fluctuations and interactions and correlation driven by these dipole-dipole interactions. So if you were to consider a smaller length energy scale, for instance, the spin system, these spins tend to align each other or anti-align each other by spin-spin interaction, usually the exchange interactions, and this spontaneous generation of the magnetic domain we usually observe. And this typical size of the magnetic domain is determined by spin-spin fluctuations or spin-spin interactions. Or even we can go beyond typical condensed matter subject. So this is the human SNS network of the Facebook. So we can think of the length scale as a number of jumps to move from one node to the other. And this number of jumps we can think of as an effective length scale, and it characterizes how much each networks are tightly winded together with each other. Okay. So this is also one kind of thing. If we were to consider many body system, then typically more than two length scales start to compete each other. The well-known example is the three-dimensional Fermi gas with the attractive interaction, also known as a BEC-BCS crossover. So here, two length scales compete. So one of them is the interparticle distance, which is given as 1 over Fermi wave vector, while the another is the binding size. The binding size, if binding size is smaller than the interparticle distance, 1 over Fermi wave vector, then we can think of the two electrons as the effective composite boson. And the ground state of such a system is described by Bose-Einstein condensate. High temperature phase is characterized by Bose liquid or Bose gas. While if the binding size is larger than 1 over Fermi wave vector, we may not be able to think of this system as an effective pair of the electron. So really, we should think of these electrons as a weakly paired together. So ground state is given by BCS ground state, while the high temperature phase is the Fermi gas or Fermi liquid. So really main lesson here is that depending on which length scale dominate one to the other, the really physics that we see is very different. In usual solid state lattice, we have this fixed lattice distance determined by this elementary lattice spacing. However, if we think of a misaligned bilayer of such a system, then we find this kind of beautiful moire pattern, and this moire pattern and moire length scale merges. And it is very interesting that in principle, by changing the twist angle between the two layers, we can amplify this moire lattice spacing almost up to the infinity. Okay? This is quite useful in controlling the electronic structure of the given material. So it has been very popular after the discovery of the superconductivity in twisted bilayer graphene system. And this kind of moire material platform has been extended to many different metamaterial platforms. So for instance, this bosonic crystal, an acoustic material, or even one can control the circuit property of the classical circuit by considering this moire coupling between the two circuit chips. But here, today I would like to talk about what happens if we consider a moire of the spin system. And I want to really construct the theory of the moire twisted bilayer magnet. That's the basically direction I want to talk about. So before I talk about the spin system, it would be quite instructive what happens in the physics of the twisted bilayer graphene. So this is the phase diagram that I will draw as a function of the twist angle. So starting from the zero angle, we have this aligned bilayer graphene, and we start to rotate one of the layer by small angle, and we find these moire patterns. And as Professor Aliasani explained very well, exactly at 1.1 degree, which is known as a magic angle, this interesting superconductivity and correlated insulator phase are found. So these are very well explained in previous talk, so I will not talk about this, but taking this magic angle as a reference point, we can change our angle. So for instance, if we consider small angle limit below 1 degree, what happens is that rather than we find the change of electronic structure, we first find the deformation, large deformation of the atomic structure, which spontaneously form a domain or of this is moire atoms. So these carbon atoms locally rotate to form domain or. And in the given domain or, the electronic structures are described by this network edge states. So this network of the edge states. Or we can think of the large angle limit. So question is what happens if we consider large twist angle? The largest twist angle will be the 30 degree. So exactly at the 30 degree, you see this kind of interesting pattern. Okay? This pattern follow a C12 rotational symmetry. But we know that from the conventional crystallography, any two-dimensional periodic system can only have two-fold rotation, three-fold rotation, four-fold rotation, six-fold rotation. C12 rotation symmetry is forbidden in typical crystallography. So what happens here is that we have C12 rotational symmetry with the sacrifice of the translations. The result is a quasi-crystal. Okay? And if we look up what would be the interesting electronic state here, then we find these electronic states that are neither localized or extended. And they show this fractal pattern, which is known as a critical state. So this is very similar to the three-dimensional electronic states of the three-dimensional endless localization prediction. So these are why we call this state as a critical state. So it will be interesting if what do we observe in the case of the twisted graphene and twisted bilayer magnet. So in the small angle limit, I will explain of course, but in the small angle limit, we also observe the domain of physics. So here, as we lower the twist angle, we will also observe the magnetic domain of the twisted bilayer magnet. And these are indeed experimentally also observed and also theoretically well understood. Another feature is the large angle. We have this non-trivial topology appears. As I will explain, also in the twisted bilayer magnet, we will observe this fermion-like behavior, which will be explained by this topological physics. But nevertheless, in the case of the twisted bilayer graphene, probably the most interesting feature is the flatband physics at the magic angle. However, in the case of the twisted bilayer magnet, the flatband physics is really not understood yet. So this will be the interesting direction to study. One may think of, okay, maybe twisted bilayer magnet magic angle and twisted bilayer graphene magic angle will be very similar. So we may expect a very similar physics. But I want to mention that there will be big difference. First of all, in the electronic system, electron is a fermion, so they have a Pauli exclusion principle. So they have this Fermi energy, well-defined Fermi energy near the Dirac point. So relevant energy scale, energy level of the graphene system is this zero energy, where the Dirac point sits. Nevertheless, in the case of the magnonic system, spin system, magnon is boson, so we don't have Pauli exclusion principle. So the relevant energy scale, relevant energy level will be the ground state, which is the gamma point. So the question will be, can we make the flatband using this gamma point band structure? So that will be the difference between twisted bilayer graphene and twisted bilayer magnet. So the material that I'm interested in this talk is something called as a chromium triiodide. So for those of you who are not very familiar with this material, let me give a very brief teaser. So chromium triiodide has shared a very similar structure with the graphene. So in graphene, carbon atoms have this honeycomb lattice. In the case of CrI3, chromium atoms have a honeycomb lattice structure, and they carry localized magnetic moment J equals 3/2. So they are basically a honeycomb magnet. Okay? Nevertheless, in terms of the symmetric perspective, they are quite different because this iodide atom breaks the invergence symmetry. Due to this structural symmetry, if we look at the excitations, in the case of the graphene, we know that there is a Dirac point. If we look at the neutron scattering data of the CrI3, we also observe the similar Dirac cone-like behavior, although there are a small mass gap is observed here due to the invergence symmetry breaking. So what I want to mention is that CrI3 monolayer and graphene monolayer, they have a very similar band structure in terms of the magnon and electrons. Nevertheless, there is a very big difference in the case of the magnet, what is called as now stacking dependent magnetism, which is very well understood now in both experimentally and theoretically. Basically, what happens here is that depending on the stacking structure, this interlayer interaction between the two layers can be either ferromagnet or anti-ferromagnet. So for instance, in the case of this AB structure or BA or AA structure, three layer stacking, the top layer and bottom layer interact they make a ferromagnet, bilayer ferromagnet. On the other hand, if we look at these three different stacking, AB prime and AC prime, then two layers make an anti-ferromagnetic structure. So if we were to write the spin Hamiltonian of such a system, then we can write down our simplest model where we have intra-layer coupling, which interacts through the negative J, the ferromagnetic coupling, intra-layer coupling, and we have an interlayer coupling. But this interlayer coupling term will be a function of the relative displacement between the two nearest chromium atoms. The question is, what happens if we consider the twisted bilayer of such a spin system? Without even showing the numerical result, that you already observe that very interesting result, because in a given moire unit cell, we simultaneously observe different stacking structure. So within a single unit cell, we will find both ferromagnetically coupled region and anti-ferromagnetically coupled regions. So to confirm this conjecture, we have performed the first principles calculation. So Professor Myung-Jun Han's group in KAIST, so they calculate the super exchange coupling, which is the dominant exchange coupling between the chromium atom by varying the displacement between the two atoms. So they push these atoms and they calculate the chromium interaction. So this is the interaction. And we take these data and build a very large scale effective classical spin model. And this spin model, I will show the data. So here, these blue regions are the regions where interlayer coupling with the ferromagnetically coupled interlayer coupling, where this red region corresponds to anti-ferromagnetic coupling. So first of all, in the background of the ferromagnetic coupling, we find the anti-ferromagnetic local patches. Okay? So we find the existence of the both ferromagnetic coupled and anti-ferromagnetic coupled. And here, upper triangle and lower triangle represent the A and B sublattice. So if you see these regions, you can see strong AD sublattice symmetry breaking in atomic scale. So this is the signature of the emergence symmetry breaking that are driven by non-zero twist angle and the existence of the non-magnetic iodine atom. As I explain later, this emergence symmetry breaking plays an important role in determining magnetic grounds. So using this large-scale spin model, we have performed the Monte Carlo simulations. These are the data. So this blue region, blue line corresponds to CRI3 line. And as we change the twist angle, we find the three different magnetic phase. For instance, in angle larger than 7 degrees, we find the collinear ferromagnet. So these two layers basically have a ferromagnetic. This occurs why? Because in average, ferromagnetic coupling is more dominant than anti-ferromagnetic coupling. However, as we lower the twist angle below 7 degrees and larger than 4 degrees, we find this non-collinear domain. And what happens here is that top layer make a 90-degree rotation and bottom layer also make a 90-degree rotation to form an anti-ferromagnetic local patch. And below 4 degrees, we find that rather than two layers make a 90-degree rotation, only one of the layers make a 180-degree rotation to form an anti-ferromagnetic region. This occurred why? Because in the energetic level, it is more energetically favorable that two of the layers make a 90-degree rotation simultaneously than one of the layers make a 180-degree rotation. So this is why this LCD phase occurs in the larger angle. So this is the cartoon picture, and in the upper picture you can see the spontaneous generation of the magnetic domain. So this top picture will be the more realistic one. And in the phase diagram, if we lower the intra-layer coupling, you can see this SK phase, which is a Fermi phase. So this Fermi phase is quite interesting in terms of the conventional spintronics point of view. Why? Because it has been known that standard recipe for the fermion spin system is a exchange interaction, and we need the BM interactions with the I should say electric field. So really point is that we need very strong invergence symmetry breaking BM interaction. But in this twisted bilayer magnet, what we can observe is that by making non-zero twist angle, which breaks the invergence symmetry, as a consequence, we can realize this fermion without any BM interactions. So this modulating interlayer coupling can replace the role of the BM interactions. So why this kind of magnetic domain occurs? The reason is that basically, in terms of geometry, as we lower the twist angle, what happens is that you often the size of the moire itself become larger. Okay? So there are two typical energy scales compete each other here. So one is the interlayer coupling. When we consider the magnetic domain, then we have this interlayer coupling, which is proportional to the area of the domain. Okay? And then we have another competition that is intralayer coupling, which is the gradient energy, which is the cost of the having magnetic domain. Is proportional to the length of the moire itself. So even though interlayer coupling is very small, as we lower the twist angle, this interlayer coupling, which is proportional to the area of the moire itself, will be eventually dominate over the interlayer coupling, which is proportional to the length of the moire itself. This is quite important in terms of the van der Waals material point of view, because it means no matter how small interlayer coupling we have, if we lower our twist angle small enough, then we will always observe this kind of magnetic domain. So this magnetic domain would be quite universal as long as we have this stacking dependent magnetism. And I should mention that this stacking dependent magnetism is quite often found in many other different materials. It's like the time is out running. So I will not go over the detail of these phase transitions. So here we find these three different magnetic phases, and I didn't explain it, but somehow this pointer is not working there. In between this collinear ferromagnet and non-collinear domain, we also could identify the nature of the phase transition. So it is driven by second order phase transition. First one is this is one is driven by first order phase transition. I don't have to work. So after explaining this magnetic phase and the phase transition, also what I should explain is what would be its excitation spectrum. So what would be the excitation spectrum of these magnons? So to explain the magnon spectrum, what we do is the Holstein Primakov transformation. So the given complex energy landscape of this magnetic spin manifold, we can quantize this magnon excitations, can derive this magnon excitation using the Holstein Primakov transformation. And usually, it has been well known that in the case of the graphene, interesting excitation is Dirac cone, but also we will observe this Dirac magnon in the CRIC case. But the important point here is that in contrast to the electronic Dirac cone, which is protected by inversion times time reversal symmetry, but in the case of this Dirac magnon, we have identified that this collinearity and valley decoupling and inversion symmetry, the presence of these three symmetry can only protect the Dirac cone. So breaking, 1 minute. So breaking of one of these symmetry will make any kind of some interesting kind of topological magnon. Okay. Yeah. Okay. So These are the magnon gap diagram that we draw as a function of the twist angle and intra-layer coupling. We find many different gapped magnonic phase, and they correspond, for instance, in the case of the ferromagnetic region, we could identify the high order topological magnonic state here. So these topological magnons are described by the zero-dimensional localized magnonic state. And in this domain mode phase, we find that there is a non-trivial Chern number inside the magnetic domain and outside the magnetic domain. So as a consequence, region in between the inside and outside the magnetic domain, there will be this edge mode flowing magnetic excitations. Due to the time limit, I think I cannot go over the many of them. Sorry about it. Sorry about failing managing the time. I think I will skip the CRIs. I will assume many of them. Let me just briefly explain what happens in the case of the CL3, which is the very close family of the CRI3. The important difference between CRI3 and CL3 is that in the case of CL3, they have this single ion anisotropy pointing in plane direction. So rather than spins are pointing G direction, usually in the case of a CL3, they point the XY direction. So what would be the interesting states in the CL3? My take-home message is that in the case of CRI3, we have this Fermion excitation, but in the case of CL3, we have this magnnon excitation characterized by half Fermion number. So it's a fractional Fermion. It is indeed known that in the case of CL3, these magnnon-like topological excitations are often observed. But the caveat of this observation is that as long as we have these localized magnons, these magnon and anti-magnons are not stable, so they usually undergo these pair annihilations. But as a consequence, they only exist as a form of the metastable phase. Our idea is that if we consider bilayer of such material, twisted bilayer of such material, we can track the magnon and anti-magnon in a different magnetic domain. But as a consequence, as long as these magnon and anti-magnons are formed, and there is a too high energy barrier that this magnon can tunnel and to pair annihilate anti-magnon. So this is the main idea. So this will take a 30 seconds. So I will show the movie. So this is the example of the magnon pair as I lower the energy. So this is the energy optimization. So left picture is the top layer magnet and right picture is the bottom layer magnet. So as I lower the energy, as I optimize the energy, we can find this spontaneous generation of the magnetic domain. In addition, we observe these magnons and anti-magnon pairs. And as I lower the energy more, these magnon and anti-magnon often pair annihilate and they disappear. But what you can see is that these two pairs also pair annihilate. But these two pairs, magnon and anti-magnon, they are locked in a different magnetic domain. So as a consequence, they can exist as a stable fractional topological excitation. So that is the main take-home message that I want to mention. And unfortunately, I didn't have time to talk about the flatband. Let me give the summary. So in this twisted bilayer magnet, as a function of twist angle, we can expect this interesting non-collinear magnetic domain and magnetic domain phase. And these magnetic domain phase are characterized by non-trivial Chern number. Also, we can host these Fermion-like excitations. And if we were to consider like a CL3, which is XY magnet, we also expect this interesting magnon-like a fractional topological excitation. So that will be end of my talk, and thanks for listening.
One question.
You shown us a theory with exchange interactions, but for these dominant walls, as usual, I think the question arises whether they are block type or nail type dominant walls. So, and this usually is fixed by some like Zelashinsky-Marie or dipolar interaction. How you judge about this in your research?
Oh yeah, thank you for a very interesting question. So first of all, I should mention that in this spin model, we did not include any DM interaction. So this is purely driven by Heisenberg interaction. That is interesting because only Heisenberg interaction can make us Fermion. Of course, as you mentioned, there are many different types of magnetic domain, and their energetic levels will be determined by the inclusion of the DM interactions. Of course, the computational level determining the DM interactions in first principle manner is quite difficult.
Okay, so any question in draft and node? No? So, yeah. Any question here? Any other question? If not, so let's have the speaker again.